What would a line of a slope equal to 0 look like?
Peak or a trough, crest or a trough.
Okay, I was going more generically, flat line. So if I have something that looks like this, at this point right here, it's flat, at this point right here, it's flat. So my slopes would be 0, and we have gone through this, something that's very similar to this. In this region right here, is that a positive slope or a negative slope?
Positive.
In this region right here, and then here. So basically, that's what it looks like. This is a sine wave. Let's just say sine of x. This is a cosine wave. So if this is my position versus time, this would be my velocity. So if I have this, what would the slope look like? Well, it's 0 here, here, and here. 0, 0, 0. In this region right here, positive or negative?
Negative.
In this region,
Positive.
it looks a whole lot like that, except it's a negative sign. That's a minus sign there, not as a straight mark. So it is a function so that when I do the slope of the slope, I have the negative of pretty much what I started with. And so we're going to exploit that in just a moment. Questions here? What would throwing a 2 in there do?
Would it double your period?
It would what?
Double your period?
It would not double it.
Cut period in half.
Yeah, it would cut it in half.
2.5.
It basically shrinks it this way. In other words, if I take this and then I do it in half the time, that was absolutely horrible. Let's see, I need to end it here. Mildly better. We'll pretend that's it. Notice it gets steeper. If I take any curve and I squish it this way, it's going to get steeper. So if I did the slope of this, it's got to be steeper. The slope is steeper, and so in essence, that 2 will double this. So this would go, and that should have gone down farther. So whatever number that is, you just bring it out front. So if y, now let's do it in terms of if x is sine of 2t, so position with respect to time, then my velocity would be 2 times the cosine of 2t, because sine produces cosine, and my acceleration. So every time I go down a level, I multiply by whatever number that is, that becomes negative 4 times the sine of 2t. Therefore, I am going to assume that my position can be described by some sort of sine or cosine function. It doesn't matter which one I pick, just pick one. I typically pick cosine because in a problem like this, I have it starting at the maximum and then I let go. So I'm going to let my delta x equal some amplitude times the cosine of some number times time. In the example over there, omega is 2. Therefore, my velocity would be a omega negative sine omega t, and then my acceleration would be negative a omega squared cosine omega t. The general pattern with the trig functions is cosine goes to negative sine, goes to negative cosine, goes to sine, which goes to cosine, and then the cycle continues. So plugging this into my equation here, I have negative k a cosine omega t equals m times negative a omega squared cosine omega t. I plug this in for my position, and I plug that in for my acceleration. Well, like a bunch of stuff that cancels out here. First off, the amplitude here. How far I've stretched it initially does not matter. Cosine, that's why it doesn't matter if you use sine or cosine, because that cancels out. And what I'm left with is negative k. Actually, the negatives cancel out, so let's go ahead and get rid of that too. So if k is equal to m omega squared is equal to k over m, or omega is equal to the square root of k over m. This omega, well, when have we used omega before?
For angular velocity.
Or speed. This is angular frequency. Now, I have not run into a case in where it matters really whether it's angular frequency or angular speed. They have the exact same units, radians per second, or SI units of radians per second. They have the same symbol. They can almost be used interchangeably. There's a philosophical difference between the two. And here's an attempt at explaining the philosophical difference. If I have a wheel here that is rotating around some central axis with an angular speed of omega. If I have a pole or something like that sitting right there, so it's sticking out, and I have a light source shining a light down, then there's going to be a shadow that oscillates back and forth. So I have some light source up here causing a shadow. As the wheel turns, the shadow is going to move back and forth. The wheel turns with an angular speed of omega. The shadow has an angular frequency of omega. So that basically is a difference in context, but for the most part, angular frequency, angular speed, mathematically are interchangeable. Let's connect it with some of the stuff we've already done. If I have position is equal to, let's just say 5 meters times the cosine of 2t, what is the period?
Pi.
Yep. Suppose it were cosine of just plain old t, what would be the period?
2 pi.
Cosine of 3t.
2 pi. 2 pi over 3.
2 pi over 3. Omega t.
2 pi over omega.
So we have a relationship here between our angular frequency and our period. The period is just 2 pi divided by omega, which would be, using this, 2 pi times the square root of m over k. Frequency is 1 over the period, which would be omega divided by 2 pi. Therefore, frequency would be 1 over 2 pi times the square root of k over n. Now recognize part of the power of this if I have a spring, and how far I stretch it down does not matter. Granted, it's an ideal spring. But I have a spring, if I pull it down a certain amount, or actually, if I apply a mass to it, I can find the spring constant. I attach the same mass or a different mass, I stretch it down farther than that, and I let go, it's going to oscillate with a predictable frequency, and therefore a predictable period. I now have a timing device. If I want to figure out what a second is, or how long it takes to go up and down, I can now start doing timings of, well, if the period is 1 second, I now can break it down into quarter seconds, because it takes a quarter second to get there, another quarter second, and then 1 second to get back to where it started. Now Galileo didn't use this, Galileo used a pendulum, but a pendulum, simple pendulum, there's some assumptions you have to make, but a simple pendulum also obeys Hooke's law to some extent, and therefore you can get a timing device with a pendulum as well. But all of this and more in the videos. I think it's time for you to rejoice on your own. Have a lovely weekend.